Welcome to this microlecture from Machine Learn Atoms series. Today we will explore how low-code tools, specifically PyCaret, can simplify machine learning model creation. By the end of this session, you will understand the basic workflow for building classification models using PyCaret. Low-code platforms reduce the need of manual programming by combining visual tools with optional coding. They are ideal for semi-technical users and are widely used in enterprises applications where speed and ease of development matters. These platforms are perfect when you don't need a fully custom-built solution from scratch. PyCaret is a Python-based low-code machine learning library that supports tasks like classification, regression, and clustering. It integrates smoothly with Python and IDEs and automates repetitive tasks such as processing and model evaluation. It's excellent for quick prototyping experimentation. PyCaret uses a modular structure with dedicated models for tasks like classification, regression, clustering, and more. In this session, we will focus on classification module, which is used for binary and multi-class classification. The PyCaret pipeline involves key steps: loading data, initializing the environment with the setup function, comparing models, and creating a chosen model. This microlecture will cover up model creation. Model tuning and development will be discussed in the next microlecture. The classification module supports over 18 algorithms, 14 performance plots, and advanced features like stacking and assembling. It also includes XGBoost, widely cited as the most popular algorithm for tabular data in studies by Kegel 2021 and Rexer Analytics 2023. For our demonstration, we will be using the dataset titled Default of Credit Card Clients, originally compiled by Yeh in 2016. This dataset contains a record of credit card users along with information that can be used to predict whether a user will default on their payment. The problem is framed as a binary classification task where the target variable indicates the presence or absence of the default. The first step involves importing the dataset into Pandas data frame. To facilitate efficient model development, we often begin with creating a random sample of the data. Sampling is useful for speeding up an initial stage of analysis, particularly during exploratory data analysis and proof of concept modeling. To ensure that our evaluation is both fair and realistic, the dataset must be divided appropriately. We partition the data into three subsets: the training set, used for learning patterns, the test set, for internal model evaluation and tuning, and the validation set, which simulates unseen real-world data for final evaluation. This structure helps prevent overfitting and allows us to gauge how well the model will generalize to new data. We split the data in the following manner. The original dataset of approximately 24,000 rows is divided into 90% of modeling, 22,800 rows. Further split into 70% training and 30% testing data, while 5%, 1,200 rows, is reserved as unseen validation data for final evaluation. At this stage, the validation set, also referred to as the unseen data, is withheld from the training process. This ensures that the model evaluation conducted at the final stage is unbiased, as the model has not encountered this data before. Next step, we initialize the PyCaret classification environment using the setup function as shown in the code example. We import all functions from PyCaret classification and call setup with three key arguments: the dataset, the name of the target column, here default, and ID session, which ensures reproducibility by fixing the random seeds. Calling setup is mandatory before using any other PyCaret function. This step prepares the data pipeline for modeling and automatically configures key settings. Identifies tasks such as data splitting, preprocessing, and encoding, making it easier to proceed with the model comparison and training. Once setup is excluded, PyCaret displays a table summarizing how it processes the data. Here we see the original data set contains 22,800 rows and 24 features. It is automatically split into 70% training and 30% testing. Stratified k-folds cross-validation is used by default with 10 folds. After executing the setup function, PyCaret provides a detailed summary table that outlines how the dataset has been interpreted and proceeded. One of the most powerful aspects of this process is that PyCaret automatically detects whether each feature is numerical or categorical. In this example, we correctly identify 23 numerical features. For any missing values, PyCaret applies sample imputation techniques, the mean for numeric features and the mode for categorical ones. However, users can customize this behavior. PyCaret supports several other imputation methods such as median and zero for numeric data, or a constant value for both numeric and categorical features. These options can be specified in the setup function through the parameters numeric imputation and categorical imputation, offering flexibility to align with specific data characteristics our modeling goals. In addition to analyzing the features, PyCaret also inspects the target variable. It determines whether the task is binary or multi-class classification, and automatically encodes string-based categories into numeric labels, such as converting yes and no into 1 and 0. Overall, this output gives us a clear view of how the data has been prepared. With the environment now fully set up, the next step to compare various machine learning models. PyCaret allows us to do this efficiently through the compare models function. This key function automatically trains and evaluates a suite of models using stratified 10-fold cross-validation. The result is a comprehensive score grid that displays key evaluation metrics for each model. These include accuracy, AUC, area under the curve, recall, precision, F1 score, kappa, and Matthews correlation coefficient, abbreviated as MCC. This process provides a fast and effective way to determine which models perform best on a given dataset according to the metric that matters most for the task at hand. In our example, we observed that the gradient boosting classifier achieved the highest overall performance. It reached an accuracy of 82% and AUC of 0.78, which indicates excellent discrimination ability. Through its recall is moderate at 37%. Its balance, precision, and F1 score make it the most promising candidate. The rich classifier, in contrast, had a notably low recall of 15%, suggesting it misses a large number of positive cases. This could be problematic in context where identifying all positives is essential. The random forest classifier also performed well, with strong accuracy of 81% and an AUC of 0.77, indicating that it is a reliable alternative to gradient boosting. Once the best model is selected by PyCaret, automatically assigned to the variable best model, we can inspect its internal parameters and configuration. This is shown in the lower part of the slide. Here we see a detailed list of the model's hyperparameters, such as the number of estimator, learning rate, loss function, and other settings. This transparency is particularly useful for further model tuning, reproducibility, and documentation. While the compare models function helps us identifying the best performing model from a board selection, the create model function is used when we want to train specific model of our own choosing. This is particularly useful if we are interested in working with the model that wasn't selected as the best, or if we have performed algorithm based on domain knowledge or project requirements. Once we decided on the model we want to explore further, we use the create model function to build in. This function trains and evaluates the selected model using cross-validation and prints a detailed scoring table. The input includes performance metrics such as precision, AUC, recall, F1 score, kappa, and MCC for each fold, which are then reached to assess model stability. An important advantage of this function is that it also displays the model's hyperparameters, which are critical when preparing for tuning, assembling, or deployment. Unlike compare models, which only expose the setting of the best model, create model provides full control and visibility for any model you choose to build. In PyCaret, create model is considered one of the most granular and foundational function. It forms the basis for many advanced tasks in the machine learning pipeline and supports full customization. Moreover, users can specify the number of folds used in cross-validation through the fold parameter, allowing for flexibility based on the dataset size or computer time. This slide presents a practical example of how the create model function is used to train and evaluate a specific model, in this case a random forest classifier. As shown in the code snippet, we create the model by calling create rf. This function triggers the training process using 10-fold cross-validation and returns performance metrics for each fold. The scoring table summarizes the results across all folds, providing us with a detailed view of the model's performance. The key metrics reported here include accuracy, AUC, recall precision, F1 score, kappa, and MCC. Each of these given insights to different aspects of the model's predictive power. Looking at the average row, we can see that the random forest model achieved an accuracy of 81%. This indicates that overall the model correctly classified a high proportion of cases. The AUC, or area under the curve, is 0.77, which shows the model's solid ability to discriminate between positive and negative classes. However, the recall score is only 38%. This is relatively low and suggests that the model is correctly identifying only a minority of the actual positive cases. In practical terms, this means that while the model performs well in terms of overall classification, it has limitations when it comes to detecting all true positive potential concern in risk-sensitive applications. On the positive side, the standard deviation across folds is low, indicating that the model's performance is consistent and stable. This consistency across the different validation sets adds credibility and reliability of the model. Here we see an example of using the createModel function to build and evaluate rich classifier. The model achieved average accuracy of 80% and a notably higher precision of 73%, indicating that when it predicts a positive cases, it is usually correct. However, its recall is significantly low, only 15%, which means it fails to detect a large proportion of actual positive cases. This trade-off suggests that the model may be suitable in scenarios where minimizing false positive is more important than identifying all true positives. For example, in applications where false alarms carry a high cost. Overall, the rich classifier delivers consistent accuracy and precision across faults, but its limited ability to capture positive cases highlights the need for further tuning or alternative modeling approach if recall is a critical priority. In this example, we use the createModel function to build gradient boosting classifier, which was automatically selected as the best performing model by PyCaret during the model comparison phase. The evaluation results confirms this decision. The model achieved the highest average accuracy at 82% and a strong AUC of 0.78, indicating solid overall performance in distinguish between classes. In addition, both precision and F1 score are well balanced, which reflects the model's consistency across multiple validation faults. However, the similar order classifier, the recall remains relatively low, only 37%. This indicates that the model misses a number of actual positive cases, which may be a limitation depending on the specific use cases. Despite this model demonstrates stable and reliable performance as seen in the low standard deviation. Thanks to its balance of high accuracy, AUC and precision, the gradient boosting classifier represents a well-tuned and effective choice, especially when precision is more critical than sensitivity. Nevertheless, further tuning may be needed if capturing more positive cases becomes the main objective. This concludes our session on low-code model creation with PyCaret. We explored the core steps from data preparation to build models. In the next microlecture, we will dive into tuning, blending, and deployment. Thank you for your attention.